public health research, we are often interested in understanding how two continuous variables are related. For example, does blood pressure increase as BMI increases? Do cholesterol levels rise with age? To answer these questions, we use scatter plots, correlation analysis, and simple linear regression. First, we load three packages: readr to import data, dplyr for data management, ggplot2 for visualization. Then we load our dataset. We start with a scatter plot. On the x-axis, we place BMI. On the y-axis, we place systolic blood pressure. Each dot represents one person. This visual allows us to quickly assess whether there appears to be a relationship. If the points trend upward as BMI increases, that suggests a positive association, meaning higher BMI may be linked to higher blood pressure. The alpha equals 0.5 just makes the points slightly transparent, which helps when dots overlap. And theme underscore minimal gives us a clean, simple design. So what do we observe in this plot? As we move from left to right, BMI increases. As we move upward, systolic blood pressure increases. Overall, we can see a positive association between BMI and systolic blood pressure. In general, individuals with higher BMI tend to have higher systolic blood pressure. The cloud of points slopes slightly upward, which supports this positive linear relationship. However, the relationship is not very tight. There is substantial variability in blood pressure at nearly every BMI level. For example, around a BMI of 30, systolic blood pressure values range widely, roughly from the 80s up to 140 or higher. This suggests that while BMI is associated with blood pressure, it does not fully explain differences in systolic blood pressure. Other factors such as age, medication use, physical activity, and genetics likely contribute. We also see a few outliers: individuals with very high BMI values or unusually high systolic blood pressure. In summary, this plot demonstrates a modest positive linear relationship between BMI and systolic blood pressure. As BMI increases, systolic blood pressure tends to increase, but with considerable individual variation. Next, we calculate the correlation coefficient between BMI and systolic blood pressure. Correlation tells us the direction of the relationship, positive or negative, and the strength of the linear association, from -1 to +1. A positive value means as BMI increases, blood pressure tends to increase. A value closer to 0 would suggest a weak relationship. We use use equals complete.obs to ensure we only include participants who have both BMI and blood pressure recorded. What do we have here? We see a correlation coefficient of 0.2509, or approximately 0.25. What does this indicate? Well, this indicates a positive relationship between BMI and systolic blood pressure. In other words, as BMI increases, systolic blood pressure tends to increase as well. However, a correlation of 0.25 is considered a weak to modest association. It suggests that while there is a tendency for higher BMI to be associated with higher blood pressure, the relationship is not very strong. If we square the correlation coefficient, 0.25 squared is about 0.06. This means BMI explains roughly 6% of the variation in systolic blood pressure in this sample. The remaining variation is due to other factors. So overall, the correlation confirms a positive but modest linear relationship between BMI and systolic blood pressure in this dataset. Now we take it one step further with a linear regression model. By running LMSBP tilde BMI, this gives us an intercept, a slope coefficient, a p-value, and an r-squared value. The slope tells us how much systolic blood pressure is expected to increase for every 1 unit increase in BMI. If the slope is positive and statistically significant, That provides evidence that BMI is associated with blood pressure. We have a lot to unpack from this result, so let's dive right into it. Starting with the regression equation. Predicted SBP equals 86.89 plus 0.4767 times BMI. The intercept, 86.89, represents the predicted systolic blood pressure when BMI is 0. While a BMI of 0 isn't realistic in practice, the intercept serves as the baseline level of SBP in the model. The slope coefficient for BMI is 0.4767. This means that for every 1 unit increase in BMI, systolic blood pressure increases by about 0.48 millimeters of mercury on average. So for example, a 10-unit increase in body mass index would be associated with roughly a 4.8 millimeters of mercury increase in systolic blood pressure. The p-value for BMI is less than 2 times 10 to the negative 16, which is far below 0.001. This indicates that the relationship between BMI and systolic blood pressure is statistically significant. We can reject the null hypothesis that the slope is equal to 0. Looking at model fit, the R squared is 0.0629. This means BMI explains about 6.3% of the variation in systolic blood pressure. While the relationship is statistically significant, the amount of variance explained is relatively small, suggesting that many other factors contribute to blood pressure. The residual standard error is 13.92, meaning that, on average, observed systolic blood pressure values differ from the predicted values by about 14 millimeters of mercury. That indicates considerable individual variability around the regression line. Finally, the F statistic is 500.4 with a p-value less than 2.2 times 10 to the negative 16, confirming that the overall model is statistically significant. In summary, BMI is a statistically significant predictor of systolic blood pressure, and higher BMI is associated with higher SBP. However, BMI alone explains only a modest portion of the variation in blood pressure in this sample. Finally, we overlay a regression line onto our scatter plot using Guillaume_smooth method equals LM. This line visually represents the linear regression model. The shaded area around the line is the confidence interval. It shows the uncertainty around our estimate. This combined plot makes it easy to communicate results to both scientific and non-scientific audiences. And that brings us to the end of the lesson. In this video, we explored how to examine relationships between continuous variables using scatter plots, correlation, and simple linear regression. We learned how to visualize trends, measure the strength of associations, and interpret regression results in a public health context. These methods are essential for understanding risk factor relationships and identifying patterns that can inform prevention strategies and population health interventions. In the next video, we will move from statistical relationships to core epidemiologic measures and learn how to calculate and interpret incidence and prevalence using real public health data. If you found this video helpful, be sure to subscribe and continue the series as we build practical career-ready skills for public health data analysis using R.